Okay, so we looked at MapReduce in the previous lecture. We talked about sort of parallel algorithms first. We looked at sort of analyzing the amount of work being done in the algorithm and the depth of it, which sort of reflects how much parallelism or what the time to solution was. We had a quick introduction to Spark. I will revisit Spark during subsequent lectures. I covered enough for you to do the first assignments. I'm going to switch over to a more theoretical lecture today, and then we'll come back to some more direct implementation aspects as well. So yeah, that's what we have done. Today we're going to focus on MapReduce. We're going to pick up two very simple examples of matrix multiplication and the similarity join, which I just described, which is your second problem for the assignment. But more specifically, we're going to look at the complexity of complexity theory and how we analyze MapReduce algorithms themselves. So you can notice, like I mentioned, that it might seem very simple that you can just pick there's a map function and there's a reduce function, but what is the complexities and how do you actually make the right choices so that you can figure out if something that you're going to execute is going to take 1 hour to complete or it's going to take 100 years to complete. Okay? I lost it. Okay. So this is, and I produce this sort of a partition, right? The individual portions out here are going to be where? Are local to each process, right? So the reduction when it's happening is happening at the level of this index. So you have sort of two indices. Let me call this I, and within each of them you're going to have the small I, which is the actual index into the array itself. Okay? So depending on how you've partitioned it, you're only going to specify the coarser index out here. Okay? Like I said, just hang on a minute. In the next few slides, it should become a little bit. Yes. So this is the 2-pass stage. So I produce this key value pair where I have J and then I have these identifiers, right? So for each entry, I'm producing this value. The reduce stage for each J, so it's going to collect n of these J values, right? Sorry, n values each grouped by the J, and it's going to gather them together and produce a new key, which is going to be Ik with Mij Jk.
So you're doing the multiplication of...
I'm only doing the multiplication. But do you see why?
summation.
Why is this different from the other one? So let me...
You're not doing them at the same time, right?
You are generating all possible pairs. So in the first case, if I took this row and this column, right? So I and K, right? Now, if I consider the 2-pass method, I generate each of these values. They are gathered. So I have two n values, n and n values, which get gathered at the reducer with index J, which is the common shared index for both of these, right? Then for each combination that I have, I'm going to generate all possible multiplications out here.
And that's when you have n again, rather
Yes,
than 2n,
exactly.
because you've combined them.
I've combined them and those get emitted. So that's why, so for each of these J's, I'm generating Ik, Mij, and Jk. So the product is done. I'm not actually doing the summation because the summation happens separately. I'm producing different sets of pairs for each of these. That's why the second map stage is just the identity. And there's a separate reduction where all of these with the same common Ik index are reduced together to produce the final solution.
So for this matrix example, you're saying it's 2n and then it's n, right? But that's just for one row and column. Like
No. Well, it's replicated.
Are we assuming you're doing all of the different rows and columns, like
In
the
parallel.
pairs in parallel?
In
Yeah.
parallel, right?
Okay.
So again, I mentioned this earlier that if you consider a single Mij out here, right? So just take one particular Mij. How many of these values need to be multiplied with it? N of these, right?
N, because each column.
Yes, so each column will need to be multiplied. So either you replicate this n times so that they can be picked up by the corresponding reducer and then done independently, or I generate one of these and for each pair of those I gather them together and multiply them separately for all possible combinations and send them out again. That's the only difference. whether you're generating the replication out here or whether this particular reduce task is doing more of a work in generating that n square combination that you would need, right?
Okay.
That's all you're doing, okay? Well, 10 to the 6. Okay, never mind. A million, right? So if I have a million, let me group it into, say, 1,000 now. Let's group it into 1,000 groups of 1,000 images each, right? Then my n square, which was a million times million, now reduces to a million, right? And each task that I have, whether it's a map or the reduce task, is operating with a more sizable 1,000 by 1,000 group of images. So what you want to do in grouping is that, so we'll start with just choose some arbitrary G and we can analytically figure out what our optimum G is, or the number of groups. So each group will have a million over G images each, and the map task is going to take input element IPI and it's going to generate GI keys. So the replication is only to every other group. Does it make sense? It's not terribly complicated. Instead of generating every possible pairs, I've created these bands and I'm saying that let me just replicate this image and pass it on to another group and not to every single image within that group, right? So how many keys am I generating for each image? G minus 1. You can treat it as G if you want it to be generic enough and treat the self-similarity as a special case. And the associated value is just going to be the I and the PI for that particular one, so that you identify the index and the specific image itself. Is this clear? No? Yes?
How are we going to group the images? Is it like random or?
It's random. It doesn't matter, right? Because I have to compute all similarities. So you can use whatever metric you want. I had 1,000 images, or I had a million images, and I'm just putting it into 1,000 times 1,000, right? So I'm just saying that group it into, say, 1,000 groups or whatever G groups of million over G images each. Now, the replication is that now instead of computing every single similarity, I'm only replicating it and passing it on to different groups. Let's say that I have a deck of cards, okay? And we want to compute similarities. I want to see if each two cards are similar or not, right? Now, I can take and give one card to each of you and then ask each of you to go around and check with everybody else, do we have the same card? That was the first case that we talked about. Instead, let's say that I had 4 decks of card. I give one deck to each of you, right? And now I can ask you to see if there is any similarity. How does the replication change? In the first case, you're going to be taking each card and comparing it with every other person out there. Here, you can take one card, replicate it to everybody else and say that here it is. So the replication is only 4 times. No?
Well, I understood it except for the replication part. Do you mean that they would, like, if he had a card, he'd pass it to us and then we'd check if we
He would
each
actually,
have it,
well,
or-
in this sense, he would actually literally create a copy of it and give it to you, but yes.
So and then we could look through
Then
our
you could,
cards
and then
just see.
do the comparison.
And then what's he doing in the meantime?
He's comparing against your cards.
Okay.
So you can reduce it further because you have this, there is a replication out there that it's a symmetric process, at least if you assume this. So, yes.
So still n square comparisons will go on, but our replication cost will be.
Yes, yes. So you're reducing the communication. You can't really do much about it, at least not this way. There are ways to handle the n square issue as well, at least if you go into the approximation space. But in this case, yes, you will do n square. Like I said, the extreme case is to have one process which does everything. The second intermediate stage is that you have one task for each process, each image, and that compares that image against everybody else. And this would be the other intermediate case. Now, in the reduce section, you have to consider what the reduce key is. And so each time, I'm going to get 2 times 10 to the power 6 over G elements, right? So where I had an n by n pairs, I have sort of divided up into a G by G grid, where each G grid gets from 2 separate entries 10 to the power 6 by G images. Right? So for each combination. So if this was my original case where I said this is 10 to the power 6 images and 10 to the power 6 images, this is the full comparison that I had to make. I have broken it up into G segments. For each of these G by G segments, I will get some subset of images here, which is 10 to the power 6 by G, and another subset out here. And I will compute the similarity between these combination of images. Does this make sense? Or does it not? Ask me a question, sorry. Yes? Is that clear or not?
So far.
Huh? So far? Okay. Yes?
Yeah, I don't know if I missed something, but we are trying to reduce the communication cost, right?
Yes.
But when we are dividing million images into 1,000 images groups, we are still trying to duplicate an image, and send over 1,000 other groups, and we have to compare them, and we need to maintain an overhead.
What overhead?
Like which images are replicated, which images are being distributed to other groups.
No, we are not, right? So think of what you're doing. You're just saying that in the first case, I would have taken each image and replicated it a million times. And now if I said that the number of groups was 1,000, I'm only replicating it 1,000 times. Right? And because I've grouped them, that individual process where originally the individual process would have received 2 images as input and compared 2 images and given a single output of whether it was similar enough or not, is now receiving 1,000 images from 2 separate sets, possibly the same set, and then doing all possible comparisons there.
So is it too simple to think of this as before we had the 2 megabytes because we were just comparing 2 images and one process was just working with 2 images at a
Yes.
time, and now what we're saying is we have the opportunity to break it into an appropriate number of groups so that each process is working with more at once.
Yes. So in this case, if I choose the example of 1,000 group, then each is
Yeah.
working with basically 2,000 images or 2 gigabytes,
And
and then it can do all of that in a more efficient fashion.
then but you can choose the size of the group depending on your application.
Application, the architecture, and what the computational complexity is going to be. So if you can fit it into memory and you can be efficient about it, then you choose it accordingly, and the level of parallelism. So you're trading off the level of parallelism for more efficient computation, right?
Okay.
And that's it. So you have to then figure out, because like I said, that there is a self-similarity case, you'll have to deal with who does this in terms of when you have pictures which belong to the same group. So in this case, for example, it's the same group in both cases, so the diagonal blocks, you need to figure
So
out
you
who.
have to choose the groups so that they don't conflict with each other.
Yeah, and who's going to be generating so you don't generate duplicates, because you still have a single group there.
We have to figure out the top right.
This is you can design a simple heuristic of who's computing that combination. So you can always say that the second pair is going to be the larger one. So
It's symmetric matrix.
it's if you assume that it's symmetric.
I mean, similarity measures should be.
It should be, but again,
Hopefully.
but in this case you don't have to. So yeah, just a quick summary. So if we did this way and we sort of chose G of 1,000, the input would be 2 gigabytes, and now instead of having an exabyte, total communication, which is still large, it's still an n-square computation, would be down to a more manageable petabyte. Okay, and so that's basically what we are trying to do in this case. That you would choose it so that you can realistically solve it with whatever resources you have. And in many cases, if you have 32 gigs of RAM, you maybe want to up it by another factor of 10 and actually choose it up to 20 gigs instead. And so you can then choose accordingly what is going to run, and then choose the right level of parallelism. So we analyze this, and we talked about. So we considered a few examples, and we were talking about analyzing the complexity, which basically for the most part boiled down to the communication costs involved in MapReduce. So we're going to sort of continue with this and formalize this a little bit more and see what are the lower bounds. So this is, it's going to look very similar, but it's a slightly different flavor in the sense that we're trying to say that yes, we have picked one particular style of an algorithm. Can we, of course, we can use the same analysis to compare them, but more importantly, what is the lower bound for this, for the best possible implementation of analyzing or performing the computation in that particular way? So, in the simplest sense, when you consider a map-reduce algorithm, you have a set of inputs and a set of outputs. And so we think of these as the map task as associated with inputs, and then we think of the reduce task associated with the outputs, that there is some one or more outputs being generated at each of our reducers. Okay? It's somewhat of a simplification, but it's not too far from truth. So you're going to have relationships of this sort. So you're going to build this kind of a bipartite graph where each key that gets generated by the map tasks are sort of represented by these arrows, and the way they get collected on the reducers are forming the other end of the edge. Okay? So the way we go about analyzing, so this is a graph of this sort is easy to build or to at least analyze. So what are we interested in? We say that we start with a reducer size Q. And for those, does everybody remember the two factors that we talked about, the reducer size and the replication rate? The reducer size was the maximum number of inputs that we would expect at any given reducer. And the replication rate was that for any input that a mapper receives, how many times does it replicate it? So in this case, the replication rate is 3, and the reducer size is 2 in all cases. Okay? Does that make sense? Just a quick refresher. So, like I said here, you start with an assumption that you have specified a reducer size Q, and that's the maximum that any of your reducers can get. And this is sort of a very subtle point, but you should understand that for every output, there is at least one reducer that is assigned all input related to that output. Remember that we talk about one of these cases, we are really saying that there is a map and a reduce stage, and at the end of the reduce stage, you get your output. So at least one of your reducers must be able to generate one part of your output, right? Any of your output that you expect, because otherwise you can't. There is no combination if the inputs are divided across multiple reducers, because you don't have a second reducer stage in this case. So oops. Anyway, let's do this again. So we had Qi. Okay. Now I'm just saying that I know that the max of Qi over all my reducers is Q. So if I replace one of these guys by Q, then this inequality is not violated, right? Which means I can factor Q out of the summation, right? And then we can manipulate this, which basically means that the total communication that I would have would be this, right? Is that fine? So 4 is the communication from the map task to the reduce task, because the communication is effectively what? Between the map and the reduce is the total number of inputs received at all the reduce tasks. Because the reduce tasks are only going to receive what the map sent it. So this is the total communication between all map tasks to all reduce tasks. Yes? So how do we get the replication rate? I divide that by the number of.
Can you explain that?
Okay. So did you get it? Do you have this? Yeah. You get this expression. This is the inputs that all the reduce tasks receive, right? Which is the total number of keys that get generated by the map tasks. So that is the communication between the map tasks and the reduce tasks. This expression, summation of Qi. If you remember the graph that I drew initially, which is like, do you remember? So that's also the inputs that are, so the number of edges that are incumbent on the reducers is the same that originate from each of the map tasks. So the communication basically between the mappers and the reducers is this. Yes? And so now I have this. So what is the replication rate? How did I define the replication rate? As the average of this. So that's going to be divided by the size of the input. So how much did, so if this was the total number of keys generated with the total communication, then the average is that divided by P, right? So I can now change this to R divided by P. So the replication rate has to be greater than or equal to P or Q. So what is the lower bound on the replication rate? That's it, we are done. Okay? Do you understand? So this, for this particular class of an algorithm, you remember that we started off, we don't have any G here, we don't have any Q here, we don't K, we got rid of all of that stuff. So given this, and look in terms of the assumptions that we made, right? The assumptions made are very, very simple. This is only on the input and the output. It's not really, the details of the algorithm are not really here. We're just computing that what is the lower bound. If you say that I have to take this kind of an operation and embed it in a MapReduce framework, then what are we working with? So it's not, like I said, think about application, that changes, and what you're going to end up with is that replication rates are actually different, and that tells you which one should be preferred and under which conditions. So you basically get this relationship between the size of the matrix and Q. So depending, and these are typically the values that you will have control over. You know what's the size of your problem, you know what's the largest problem that one of my nodes can reduce. So then this allows you to now compute what is the better algorithm to choose for your conditions, right? For your architecture, for your problem size. So we will do this again for the matrix.